Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to talk a bit more about translations primarily, and talk a little bit about some general theory involving translations. So the first thing we'll talk about is when two maps commute. So if I have two maps, so here I'm thinking of my maps f and g as being maps, and remember, being a map means that you are a function from a set back to itself. So your domain and your codomain are the same thing. So here both f and g are maps from a set capital X back to itself. In geometry, we're going to think of the set capital X as being the points on the plane. But for now, let's just look at it abstractly. In this context, we say that two maps f and g commute if f composed with g is the same as g composed with f. And so it doesn't matter what order we do the operations in. Now, in the specific context of geometry, some isometries commute with each other and others do not. So the first observation that we have is that any two translations commute. And the reason for that really comes down to the parallel definition that we had for transformations, right? If I do a translation from A to B and then from B to C, well, basically I'm constructing a parallelogram. And then if I'm going from B to C first, and then from A to B, I'm also constructing a parallelogram. And however we arrange this, the parallelogram we get at the end, the picture we have at the end, is going to be the same parallelogram. So that's roughly the idea why that's true. We're not really going to prove it, but we'll maybe look at a picture in a little bit. The other key observation is that any two rotations that have the same center commute with each other. That one is not hard to believe, but we will not prove that either. But there are also plenty of examples that do not commute. So for instance, if I do a reflection and if I do a rotation by some angle other than 180 degrees, then in general these are not going to commute with each other. Similarly, if I take rotations with different centers, that will not typically commute. Right? There's some weird arrangements that maybe you can make things commute, but the typical arrangement of these things will not commute. And I ask you to think a little bit more about it in this week's discussion prompt. Okay, so the fact that the translations commute, as I said a minute ago, the proof of it basically follows from the Euclidean parallel postulate and the result you proved on the homework about translations being determined by these parallelograms. So the key ideas are that if I have three non-collinear points, that uniquely determines the fourth point to make a parallelogram. And then finally, translations give parallelograms, and parallelograms give translations. So let's jump over here to GeoGebra and take a quick look at that. Okay, I have here in GeoGebra, I have my points A, B, and C, and I have a point P. And I am really thinking of doing the translation from A to B, and then the translation from B to C. So the first step is I'm going to use our parallelogram idea that you saw in the most recent homework. So I want to take the line parallel to the line AB, incident to P, and I similarly want to look at making a parallelogram AB, and I'm going to call the point Q there. So let's let this parallel line like so, and then this point here is the point I'm going to call, oh, I didn't put it in the right spot. And that's now my point Q. So now I've translated P to Q, and then now I do another parallel line here, and parallel line here, and this point right here is the point I'm going to call P prime. Right, so that is the composition of this translation from A to B, and then the translation from B to C. And I'll move this point around. As you see, that works very nicely. And that's the translation from P to P prime. Now what I want to do is I want to first translate in the direction from B to C first, and then the direction from A to B. Okay, so let's do that. So from B to C first, I have to drop this parallel. Okay, there's a secret segment here. I have to put the segment PB, right? I want PB, C, and then I'm going to call this point Q prime, wherever it is going to be the translation of P in that direction. So let's do that. And this point is now my Q prime. And now we want to take the line parallel to AB, incident to Q prime, and bingo, my point lands exactly where I wanted it to, at this P prime. Right, and this holds up as I move these things around. And in order to look at this, we see we have a large number of parallelograms we can look at, and a large number of congruent triangles, right? So if you grind through that process, you will see then that this PQ, P prime, Q prime is a quadrilateral, right? So that one is going to be a very useful quadrilateral. And so that one is what's going to allow you to show that you end up with these two translations commuting with each other. So here we want to connect the idea of translations to the idea of vectors. Right? You have notions of vectors that you've thought about in the context of calculus, in the context of analytic geometry, things like that. It's a very useful framework for thinking about things. I want us to think about a vector as being the same thing as a translation. So if I think of a vector, for instance, the vector AB, I want to think of this as being essentially the same thing as, right? So I'm writing an equal sign. I don't mean equal, so I'll put it with maybe some quotation marks. That this is the same as the translation that sends A to B. So this is for this to make sense, we need several properties that have to do with vector addition, with composition of translation. So here's the most important one. We have 3 points, A, B, and C, and I don't require them to be distinct or anything at all for the statement of this theorem. T1 is the translation from A to B, T2 is the translation from B to C, and T3 is the translation from A to C. And in any of these three cases, if the 2 points are the same point, I'm going to take my map T to be the identity map, right? So if A equals B, for instance, then T1 should be the identity. And then the conclusion we have is the composition T2 composed with T1 is the same as T3. So what that means is if I go from A to B and then B to C, is the same as going directly from A to C. Okay, In these notes here, we're going to prove the case where we have, I said 3 distinct points. I really mean 3 non-collinear points. And there are multiple strategies that we could use to attack this problem. So the first observation that we have is we don't need to prove it for every point. We just need to show it for 3 non-collinear points. Right? Since an isometry, the left-hand side of our identity and the right-hand side are both isometries, we just need to check that they agree on a triangle, and if they agree on a triangle, they agree everywhere. Now, I'm not going to show it for just 3 points. I'm going to show it for infinitely many points, but it's not for every point in the plane. So we're secretly using this theorem here in order to prove a result. And in my opinion, the proof is easiest if we use the parallelogram definition for the translation, which is what you proved in the most recent homework. So we're going to use that homework fact in order to make this proof go. Okay, let's take a look at this in GeoGebra so we can see what's going on more clearly. Okay, so here we have the points A, B, and C, and I've given myself a point P. And what I want to do is I want to construct the point Q, which is the translation of P by the vector AB. And so that guy is called Q. And then I want to translate Q by the vector BC. Let's see, Q translated by BC. And this now gives me the point P prime. Okay, and what I want to show is that the quadrilateral I have here, AC P prime P, is a parallelogram. If I can prove that, then I am done. Now, the first thing we have is that this quadrilateral, and so that's ABQP, and then the other one I have is BC P prime Q. These 2 quadrilaterals are parallelograms by what you proved in the homework. And as I just said, our goal is to show that the parallelogram here that I have put in, let me put it in green. This green parallelogram here, I want that guy, that green quadrilateral, I want it to be a parallelogram. And I'm going to move my points around so that they aren't crowding each other too much. Right, so that's our goal, to show that AC P prime P is a parallelogram. And if we're able to do that, then we are done with the proof that P prime is the translate of P in the direction AC, which is what we want to show. Okay, now there are a few things that I want to avoid having problems with this. The first one is I do not want P to be incident to the line AB because that makes my life difficult. The other thing is I don't want Q to be incident to the line BC. So worded differently, I don't want P to be incident to the preimage of the line BC. And then finally, I don't want that to happen. I don't want P to be incident to the line AC. Right, so I'm taking P somewhere else. And I'm going to be using some angle arguments. And for that, I would like P to be in the interior of the angle ABC. Right, if I put it up here, I'm going to have to think a little bit more. The argument still works. I just to really think using our picture here of where things are, I'm going to ask that P is in the interior of the angle ABC. Now this isn't a problem because I only need to show this result for 3 points that form a triangle, right? Because any isometry is entirely determined by its behavior on 3 points. Okay, so I'm going to introduce a point. I'm going to draw a line here, BQ, and I'm going to have it intersect the line PP prime in a point I'm going to call X. And I'm calling it X because I don't want you to think it's important in the result. It's sort of scaffolding we have in our proof. And now at this point, we are going to look at the triangles we have that are ABC let's maybe make it in orange, and the triangle QPP prime. And maybe I'll make that in that sort of reddish color. Okay, we have a lot going on here on our picture, but we want to consider the triangles ABC and PQP prime. And my goal is to show that these triangles are congruent to each other. So the first observation is that AB is congruent to PQ because those are opposite sides of a parallelogram. Also, BC is congruent to QP prime since they're opposite sides of a parallelogram. And we have that the angles here, so ABQ and PQX, those are congruent by the fact that the line AB is parallel to the line AQ, and those are corresponding angles for this transversal PX. Right, so that's these are corresponding angles here. And similarly on the other side here, so CBQ and P prime QX are congruent because those are corresponding angles where my parallel lines are BC and QP prime, and my transversal is again this line BX. Now, these two angles together add up to give me angle ABC and angle PQP prime. And therefore, angle ABC is congruent to angle AQP prime. And hence, from side angle side, the triangle ABC is congruent to the triangle PQP prime. Okay, so good. So my two triangles are now congruent to each other. And what that now means is they're side here, AC, is congruent to the side PP prime. And now what I want to show is that AP is congruent to CP prime. But now this is going to be straightforward, because P prime was constructed by this composition of two isometries moving P, and those two isometries moving A give me C. And as you know, the composition, actually you proved it in one of your homeworks, the composition of two isometries is an isometry, and hence this segment AP is congruent to the image under the isometry, which is CP prime. So that gives me that the AC is congruent to PP prime, AP is congruent to CP prime, and therefore the opposites of that quadrilateral AC P prime P are congruent, and therefore we have a parallelogram. Right? If you recall, you proved that theorem using the alternate interior angles theorem, I guess, several weeks ago. Actually, even in the last module. And that completes our proof. Okay, good. So now that we have proved this property about translations, let's think about vectors a little bit. Right? So if I identify the vector AB with the corresponding translation that sends A to B, I want to think about these properties as being the various properties that have to do with vector addition. So for instance, what we just proved was that the vector AB plus the vector BC equals the vector AC. Right? That's saying that the composition of the translation from A to B with the translation to B to C is the translation from A to C. The commuting fact about these translations that we did not prove but that we stated, right, the translation from A to B and the translation from B to C commute with each other. That's just saying the vector AB plus BC is the same as vector BC plus vector AB. The order doesn't matter in the vector sum. Okay. There's one more operation we have on vectors that's important, and that's scalar multiplication. Now to prove the various properties of scalar multiplication, for instance, that scalar multiplication distributes across vector addition, these various properties like that, we will need to revisit after we've done some work with similarity. And similarity is going to be the topic in our last module, in module 3. Okay, that's it for this video. There is a homework problem that's a slight variation on what we proved previously, so do take a look at that. And on our next video, we will apply some of these ideas in order to solve some problems. Thank you for watching. I hope you enjoyed it. See you on the next one. Happy mathing.